In mathematics, we often start with integers. Numbers like 0, 1, and -1 are solid, isolated blocks of certainty, fixed markers on our map. But the physical world is full of partial amounts. When you need to split a measurement or divide a resource, the whole numbers leave massive gaps. These empty spaces require a different kind of precision. We fill these gaps with rational numbers. By definition, a rational number is a ratio of two integers, p over q, where q is never 0. These entities are designed to live within the fractures between whole numbers. Rational numbers provide the exact coordinates for the measurements integers skip over. They allow us to quantify the messy spaces that simple counting numbers cannot reach. To find where a rational number belongs, you have to look at its bounds. This is essential for improper fractions, where the numerator is larger than the denominator, pushing the value past the number 1. To find 3 halves on the number line, we convert it to a mixed number, 1 and 1/2. This tells us to search between integers 1 and 2. The denominator divides this segment in half. The first mark after 1 is the exact coordinate. Even the most top-heavy fraction is anchored to a specific, undeniable location on the mathematical grid. Rational numbers have a deceptive quality. A single coordinate on our map can be represented by many different numerical names. We simply call these equivalent rational numbers. You can create them by multiplying both the numerator and the denominator by the same integer. Look at -2/5 on the line. This is its fixed position. Multiply top and bottom by 3, it becomes -6/15. By -4, it's 8 over -20. By 10, -20/50. The labels change, but the value remains where it started. You can reverse this by dividing both the top and bottom by their common factors. This strips away the extra layers and reduces the fraction to its simplest, standard form. Equivalence allows us to adjust a number's appearance without altering its value. It is a necessary step for making fractions compatible so they can interact. Adjusting a number's appearance is critical when comparing two mismatched rational numbers, like 3/4 and 5/6. These fractions use different denominators, meaning they are built on different scales. You cannot tell which is greater just by looking at the raw numerators. To compare them fairly, we need to find a common denominator. We do this by calculating the least common multiple, or LCM, of the two denominators. For denominators 4 and 6, the smallest number they both divide into is 12. This is our shared baseline. Now we rewrite both. 3/4 becomes 9/12 and 5/6 becomes 10/12. Since 9 is less than 10, we definitively see that 3/4 is smaller. Standardizing the denominators removes the visual confusion. It allows us to rank and order any set of numbers with absolute certainty. Matching denominators allows us to perform addition on previously incompatible values, merging two distinct numbers into one. Consider the sum of the mixed number 1 and 1/4 and the negative fraction -2/3. First, we convert 1 and 1/4 into the improper fraction 5/4. Next, we find the LCM of the denominators 4 and 3. That shared baseline is 12. We multiply to match that base. 5/4 becomes 15/12, and -2/3 becomes -8/12. With the denominators harmonized, the numerators can finally be combined. We keep the base of 12 and simply add 15 and -8. Adding 15 and -8 leaves us with 7. The final result of our union is 7/12. Zoom into the gap between 7/12 and its neighbor. Because we can always find a new common denominator and a midpoint, we could calculate a new fraction in that space, then another between those, and so on. This property means we can keep finding new rational numbers forever. They populate the entire number line, creating a continuous path of coordinates between the integers. By standardizing denominators and identifying equivalent forms, we can locate and combine any value across this infinite landscape.